analyzing the M+1 peak. So we can use the M+1 peak to determine the number of carbons in the compound. So let's see how we do this. A few minutes ago in the other video we looked at methane here, and we talked about that this was the M peak. We sort of ignored, and the molar mass is equal to this peak, so the molar mass of methane is 16. No surprises there. There's a little peak right here, though, that's due to the fact that not all carbon atoms have the same molar mass. So this is the M+1 peak, and it is due to the fact that 98.9% of carbon is carbon-12. That's much more common. 1.1% of carbon is carbon-13. And that's what you're seeing here. You're seeing the percentage of carbons that are carbon-13. Since methane has just one carbon in it, this peak, the M+1 peak, is 1.1% of the molecular peak. Okay, now if we have a molecule that has more than one carbon, like this benzene here, we have the possibility that this first green one is a carbon-13. But there's also a possibility that the second green one is a carbon-13, or perhaps this one's a carbon-13, or this one, or this one, or this one. So we have 6 chances that we might have a carbon-13. So this is our molecular peak, and this is our M+1 peak. Because there's 6 chances, we expect the ratio of these two to be 6.0%. So we can look at the size of the molecular peak and compare it to the size of the M+1 peak and see what the percentage is and come up with the number of carbons. So let's see how we can do this. We're going to propose a molecular formula for a compound using the following mass spec. So we don't know anything about the compound except that it has a molecular peak that appears here at 86. The base peak is here. And we also know that the percentage of carbon-13 in all carbon is 1.1%. All right, so instead of just looking at these lines, we're going to look at the mass spectrum data in a table form. And here we have the relative heights of our molecular peak and our M+1 peak. We need to know how these two relate to each other. So we're going to take our M+1 peak and divide it by the molecular peak. This will be 1.2 divided by 20.9, and we'll multiply it times 100%, and we'll get our answer, which is 5.7%. Now we know that carbon-13 is 1.1% of all carbon. So if we take these percentages and divide them, we'll get 5.2. We're going to round that to 5. So we have 5 carbons. Now we have 5 carbons, and we have a molar mass of 86. So 5 carbons are going to weigh 5 times 12 is going to be 60. So 60 of our mass here is taken up by the carbons. So our total mass is 86, and we subtract off the mass of the carbons. This is total mass. I'm going to subtract off the mass of the carbons. We'll just say carbon mass. How's that? That leaves us with 16 mass units. No, it doesn't. It leaves us with 26. That's good. Otherwise, the problem wouldn't work. All right. Now, we can't write one possibility here we need to consider is we have 5 carbons and we have 26 hydrogens. Well, we know that won't work because the most hydrogens we could have if it's fully saturated would be 12. So that won't work. We know that this is an even number, so nitrogen is not a possibility. And we know that nitrogen is not a possibility because it's not even, and we don't have enough mass for 2 nitrogens. So why don't we try an oxygen? So I've got a mass of 26. I'm going to subtract off the mass of oxygen, which is 16, and that leaves me with 10. Okay, so this is the mass of oxygen. And this mass of 10 that's left is going to be hydrogen. So our formula here is C5H10O. Okay, so that's a bit messy, but hopefully you can follow my logic. Let's do another one. We'll put 2 of them up here. You might want to stop the video and try it, and then you can watch me do it. Okay, so we need to know the relative height of these 2 peaks. This is our molecular peak, and this is our M+1 peak. We'll take our 1.7, divide it by 38.3 times 100%, and that's going to give us, I got my math worked out over here, 4.4. That's the relative height of the M1 versus the M. We'll need to divide that by the percent of carbon 13 in the environment. This one's going to work out nice and even, so we've got 4 carbons. And we're going to kind of do the same thing as we did before. I'm going to take the mass of 72 and I'm going to subtract off the mass of the 4 carbons. And that's going to give me 48 left. No, 24 left. That leaves me 24. And I'm going to look at the 24. I'm going to see that it's even, so I don't have a nitrogen. It's too large a mass for it just to be hydrogen. So we're going to take the 24 and subtract off 16 for oxygen. And we'll have 8 hydrogens. And so our formula will be carbon 4, H8O. O. Okay, so let's look at B here. So let's look at B. Here our molecular peak is at 68 and its relative height is 100%. That means that it's the base peak. This is the tallest peak on the chart. The peak right next to it is the M+1 and its relative height is 4.3. So 4.3 divided by the prevalence of carbon-13 in the environment of 1.1. I guess we could put percentages on these if we wanted to. And we will get 3.9, which is really close to 4. So I'm going to say that our compound up here has 4 carbons. 4 carbons are going to be 4 times 12. That's going to weigh 48 units. Our peak here is at 68. So if I take my molar mass and I'm going to subtract off the mass of the carbon. I'm going to take my 68, I'm going to subtract off 48, and that leaves me with 20. 20 is too many for it to be just hydrogen. We can't have 20 hydrogens parked around just 4 carbons. And it's an even number, so it's not going to be a nitrogen. The other common element that comes into play is oxygen. So let's take our 20 and we're going to subtract off an oxygen, which is a molar mass 16, which gives us a molar mass left of 4. So I've got 4 carbons. I'm going to have 4 hydrogens. And I'm going to have an oxygen. And that is my formula. So let's look at the next one. Here we have a molar mass peak at 54. This one is also the base peak, and so we already have the relative how these two peaks are associated with each other. The M+1 peak is 4.6% of the mass peak. Okay, so we'll take our 4.6% and divide it by how much carbon-13 there is in the world. And we get 4.2, which again is really close to 4. So we're going to say we have 4 carbons. And we're going to do basically the same thing. We've got a molar mass of 54. And we're going to subtract off the mass of the 4 carbons. And that's going to give us only 6 left. And so this will be hydrogens. So our formula will be 4 carbons and 6 hydrogen. Okay, so let's look at D here. We have a molecular peak at 96, and its relative height is 19% of a base peak. The M+1 peak is, of course, at 97, right next door, and its relative height is 1.5 of a base peak. We need to know how these two relate to each other. And so what we'll need to do is take 1.5 and divide it by 19. 100%. And this will give us 7.9. That's the relative height of our M1 peak versus our molecular peak. We need to then take that number and divide it by the prevailing amount of carbon-13 in the world. And if we do that, we'll end up with 7 carbons. A number very close to 7. So we'll have 7 carbons in our compound. I'm going to do the same thing I did before. We're going to start with this molar mass, and we're going to subtract off the mass of the carbon and then see what mass is left. So we have 96, and we're going to subtract off 7 times 12, and that should give us 12. That is, we can't have an oxygen. It's not possible because the molar mass of oxygen is 16, molar mass of nitrogen is 14, so we can't have either of those. So we're going to have C7H12 will be our formula.